So in lesson 57, we're going to be looking at some properties of the definite integral. And remember, that's when we integrate and we actually find an answer, a specific answer. We don't put the plus c on it, and we use our definition where we take the integral of evaluated at a and subtract the integral evaluated at b. And so this first one really is just saying if you have the integral of a sum of two functions, you can take the integral, the definite integral of that first function plus the integral of the second function. And that would also work for subtraction, because we could think of this as plus a negative, and the same idea here. We've seen this next property with just integrals, where if we have a constant in there, we just call it sliding it or bringing it out in front, and we recognize that that would work because that's similar in derivatives, and we showed why that was true a long time ago. But if you have a constant there, you can just bring that out and then take the integral of definite integral of just the f of x. Next, as you look at this one, it might look the same at first, but if you notice in this first part on the left side, you're going from A to B, and then on the right side it's from B to A. And so if you switch the order of your indexes, it's going to be the opposite of this one. And if you think through the definite integral, you would normally do the integral evaluated at A minus the integral evaluated at B. Well, now what you're going to do is going to be B minus A. So just thinking through it, if you had a 7 minus a 3 when you worked with this one, that would give you 4. Well, in this case, it would be a 3 minus a 7, which would give you, obviously, negative 4. This one takes a sum and combines it into one, but notice what's happening with our intervals here. This is from A to B, and then from B to C. And if you add those two integrals together, that would really be the same integral as if you went just from A all the way to C. If you remember in geometry, it's almost like a segment addition postulate or something like that, where you have from A to B plus from B to C will equal the whole thing. This one, this is from A to A, so thinking of that in a couple different ways. If we think of it like in terms of the definition of definite integral, you would take the integral evaluated at A minus the integral evaluated at A, which obviously will give you 0. Also, you can think of, if you're thinking of an area under a curve from A to A, that's really no space at all, so that area would be 0. A few more, and these are good for you guys to be able to learn to read and understand. This is saying if f of x is greater than or equal to 0, so that means above the x-axis or on the x-axis from A to B, then the integral from A to B will definitely be greater than or equal to 0. So as long as in the interval AB this function is above or on the x-axis, that integral will be greater than or equal to 0, and we can relate that back to area. We talked about how if the area is above the x-axis, it's positive, below it's negative. If the function is 0, like it always equals 0 on the interval A to B, then the integral from A to B will equal 0. And that makes sense again if we think of area under a curve. If the curve's on the x-axis, there's no area between it and the x-axis. And then the final part, so these three are kind of together because this is above the x-axis, greater than or equal to 0. On the x-axis, the function is equal to 0, or below the x-axis on that interval. So the integral will be less than 0 or negative, or equal to 0. So less than or equal to 0 if the function on the interval is below the x-axis. So again, I've mentioned this before, but realizing when it says a function is greater than 0, that means above the x-axis. This means on the x-axis, and this means the function is below the x-axis. These next two, well, let's just go to the next one. A function g of x is always less than the function f of x. So graphically, that just means your function, if you have a function g, it's always below a function f. Well, what does that mean? Or I should say on this interval. Then the integral on that of g of x is going to be less than the integral on the same interval of f of x. And if you think of area under the curve, obviously the area, if we went from a to b, this area here is definitely going to be less than this area here. And then if the functions are equal on an interval, then obviously their integrals will be equal on that same interval. All right, so those are the main ideas there. A lot of different properties. Most of them should make sense, and we will be referring back to these as we show different things. Here's several questions that you can think through. The question here is, here's the f from a to b. What is the integral from a to b of f of x dx? Well, if we remember these different things, this is 5, which means the integral from a to this point would be positive 5. The integral from this point to this point would be negative 10. The definite integral would be negative 10 because the area is 10. And then this would be a positive 3. So we have a positive 5, a positive 3 is positive 8, and then a negative 10, which would give us negative 2. So the correct answer for this one is C. The next one, let the integral from negative 1 to 1 of f of x dx equals 7. So the integral from negative 1 to 1 of this function is 7. From 1 to 4 is 2. Evaluate the integral from negative 1 to 4 of f of x. Well, as we think about our other properties, we had a property where if we went from negative 1 to 1, so a to b, and then b to c is really the same thing as a to c. So if you add those together, so we have a 7 plus a 2 is equal to 9, and so our answer here would be D. Moving to the next example, f and g are functions. The integral of f from 1 to 3 is 4. Integral of g from 1 to 3 is negative 1. And we want to find out what this expression would be equal to. We use a couple different properties here. First, we have a difference, so we could subtract the two integrals. The 3 could come out front when we look at this integral. I'm going to write this out. You don't always have to write the work out, but just to show you what the idea is as we think through this. Since this is a difference, we could write this as integral of 1 to 3 of this first one, 3 times f of x dx, minus the integral from 1 to 3 of the second one. All right, from here, we know that these are constants, so they can actually come out front. Again, this is our thought process. A lot of this we could do in our head, so this is 3 times the integral from 1 to 3 of f of x minus, and we can bring the 1/3 out because that's a constant, 1/3 the integral from 1 to 3 of g of x, I didn't really need that parenthesis, dx, and now we can go ahead and use these two facts up here. From 1 to 3 of f of x is 4, so really we have a 3 times a 4 minus a 1/3 times a negative 1. And so this is 12 plus 1/3, which is 12 and 1/3, so our answer there would be 9. I mean D. I don't know why I said 9. 12 plus 1/3 is 12 and 1/3, which is 12.3 continuing. I couldn't put fractions in here, that's why I put it as a continuing decimal. Next one, we have from negative 2 to 1 is 3, and then from 3 to 1 of the same function f of x is 7. Evaluate negative 2 to 3. Be careful with this one. At first you might think it's like one we did a couple ago, but this is from negative 2 to 1, and this is from 3 to 1. Well, we can combine these if it's from A to B and then B to C. Well, this is A to B and C to B. So what we're going to do is we're going to rewrite this one, and we want the integral of 1 to 3, because we normally want the smaller, the left side of the integral on the bottom. And so we can know from our one property, this was from pretty close to the beginning of our different properties. If we switch these numbers here, you're going to get the negative of this. So this is equal to negative 7. And so now thinking through this, we're going from negative 2 to 3. Well, that's going to be the same as these two combined. So negative 2 to 1 and 1 to 3. Well, adding those together, you get a 3, and a negative 7 is a negative 4. So our answer here would be D. All right, here's our last one. Assume f is a positive valued function. So positive valued and continuous, so it's greater than 0 over the interval 5 to 8. Assume also that the absolute minimum of f, the lowest value it gets is 12, while its maximum, I think I said minimum, the highest it gets is 12, and the lowest it gets is 3. Using the properties in this lesson, state the maximum and minimum values possible. All right, so let's take a look at this function f. We know that it's always positive, and the highest it can be is 12. The lowest it could be, its minimum, is 3. So this is a 3. Using the properties, what's the maximum value? So this is going from 5 up to 8. Well, its maximum is 12. So if the whole thing is 12, if it's a constant function and it's always 12, which would still be the maximum, the integral would be the area under there. And so the maximum area is really, this is 3, like this length here is 3, times 12, because area under the curve, which has to do with the definite integral. So the maximum area, which relates to the maximum value of that integral, would be 12 times 3, which is 36. So we're relating back that the definite integral does help find area under a curve. The minimum, so let's look at the minimum. I'm going to redraw this. The minimum's 3. Well, what if the minimum was always 3? If it was a constant function from 5 to 8, this isn't very well drawn to scale. Well, the area under a curve, if it was always 3, which would still be the minimum, would be, it's a rectangle, so 3 times 3, the minimum would be 3 times 3, which is 9. So the maximum that this could be would be 12, or 36. The minimum it could be is 9. And so that's properties of integrals.